Okay, so I apologize in advance for the sound quality on this video. It's probably not going to be great because I forgot my headphones today, so I'm just kind of yelling at the computer from the smart board. But either way, let's get started. This is a question from Flex that we had. It was for assignment 9.3, part C, number 2. Okay, so pull that out and look at it, read it, or this isn't going to make any sense to you, okay? This is just the graph from the question. You need all the other information. It's actually a lot like your lab that you did, except instead of it being a hit and rebound collision like you guys did, this is a hit and stick collision with some gliders on an air track. Okay, so the specific question to do with this that I got was about how do you find the mass of the target glider, okay? And it's going to come down to graphical analysis and your knowledge of the conservation of momentum, okay? So first things first, this did not look like this a second ago. I've already drawn in my line of best fit in orange here, okay? Whenever you're given a bunch of data, raw data just plotted on there, you're not ready to do graphical analysis yet, okay? What we need is a straight line for several reasons. First of all, right, you can't get the slope or area without calculus unless it's a straight line, okay? Another reason is what was the whole point of getting a bunch of data points if you're just going to pick one and then do the analysis on it, or pick two and then do the analysis on it? Why'd you bother gathering so much data, which is good, that makes a better experiment, right? Because now we can plot out all of our data and kind of take a step back and look at what is the trend in the data, right? The more data points we get, the more they start to map out the true trend, which tells us the true relationship between each variable, okay? So never begin without first drawing a line of best fit, a linear straight line of best fit. Okay, so I've gone ahead and done that. Yours might look slightly different. Again, I didn't force it through 0, 0. It just happened to go through 0, 0. Okay. So now that we've got a line of best fit, we'll move on to the idea now of what are we looking for, what equations could tell us that, and how can we relate the equations to what is on the graph, okay? So when I see something like this, my mind goes to conservation of momentum, right? As should yours. There's a collision here. We're talking about the velocity of something initially, and then we're talking about the combined velocity they move off together with after the collision, when they're stuck together as though they were one object, right? That just screams conservation of momentum. So let's start there. Let's start with just the conservation of momentum, okay? Now, like all conservation of momentum problems, we have to take all the momentum before, add it up, and set it equal to all the momentum after, okay? So if you've read the question, you know that we have a bullet glider with some momentum initially. There's also a target glider, okay, initially, and then after they get stuck together. So we can treat them as one object that now moves, well, together, right, with the same velocity, because that's what it is. So we'll call it one object. We'll say it's the target bullet glider kind of system, stuck together as one now, right? Now the question says that the target glider is initially stationary, just like it was in your lab. If it's stationary, its v is 0, and if its v is 0, its momentum is 0, because p equals mv, okay? Now let's just expand these out a bit so we can start looking at how these variables on our graph are going to be related to our requirements, right? So every p is an mv. So the momentum of the bullet glider is going to be the mass of the bullet glider times the velocity of the bullet glider. If we're looking at the initial momentum, well, then it's the initial velocity, right? So pb initial will be mv VB initial, right? This is 0. The momentum of the target bullet system after, as it moves as one object, well, it's that object, that one object's mass times that one object's final velocity, right? What's that one object's mass? Well, it's made up of the target glider and the bullet glider, so its mass must be those added together. So its mass is m target plus m bullet times whatever velocity that kind of stuck together one object, quote unquote, moves, okay? And there we go. Now, look at this. What do we have here now? Now we've got our required, the mass of the target glider, that's what we want, okay? And we've related it to, hey, the velocity that they move off with together as one object, that's our y variable. That's y, right? On our graph. That's what's on our y-axis. And hey, the initial velocity of the bullet glider, that's what's on our x-axis. Okay, now we're getting somewhere. Now we're actually looking at some kind of graphical analysis being possible in the near future, okay? But don't lose sight, it's always the same process with graphical analysis. Relate the variables with an equation, okay? Isolate your required, and then see what you do. Do you multiply y by x? Well, then you're going to be thinking about an area. Do you divide y by x? Well, then you're going to be thinking about slope, right? So let's just manipulate this for the mass of the target glider, because that's what we want to find. So can't get in those brackets yet. Remember, reverse order of operations. So this whole thing is being multiplied by that. Let's first just get rid of that then. Okay, just switch my left and right sides there. I like to have my unknown, my required on the left side. Most people do. Okay, now it's not quite isolated. There we go. Careful, don't put that in the numerator, right? This whole fraction is having this subtracted from it, not just the numerator. This doesn't belong in that fraction. Okay, and now rewrite what you got and think about how it relates to the graph. Okay, so like we said, hey, this is our y variable, right? This is our x variable. So when we solve for the mass of the target glider, it has us dividing x by y. Now this isn't quite the same as what you're used to seeing, but the idea is the same, okay? A change in x, our x variable, that's a run. So what we're doing is we're saying, take the mass of the bullet glider, right? Times it by a run, divide it by a rise, a change in y, and then subtract mb. Run over rise, right? You're dividing x by y, so it's not quite the slope. Run over rise is 1 over the slope, right? It's the inverse of the slope. It's the slope, but flipped. So really, we're saying, right, we're dividing x by y. That's just the inverse of the slope, or if you'd rather, okay? And you could pull out mb as a common factor if you wanted, but you don't need to, okay? So there we go. All we've done, take an equation we know that relates our y variable, our x variable, and our required, right? Play around with it until we have the required all isolated by itself, and then take a look. What are we doing? Are we dividing y by x? Then it's the slope. No, we're dividing x by y. Okay, that's just run over rise. That's the inverse of the slope. No worries there. We can find a run. We can find a rise. You've been doing that since grade 9 math, right? So let's go back to our graph. And let's find 2 good points, just like we always would, so that we can find the run and the rise. We're not going, okay? We're not going to use the data points. We're going to use the line of best fit. If we use a data point, what was the point of doing all those trials and getting a whole bunch of really good data and finding the trend in it? Okay, so I really like that point. That's a good looking point. It's right on a grid. I won't have to estimate. Oh, and I really like that point. That's a good one that I also won't have to estimate. Okay, let's get the rise and the run there, just like we always would. So to get from this point to this point, I run that much to the side, right? And then I rise to get from this point to that point. I rise that much on my y-axis, okay? So let's figure out what those are. I rose up to 2 meters per second from 1 meter per second, okay? While I ran up to 4.8 meters per second from 2.4 meters per second. Okay, so there we go. I've got a rise and a run. Hey, in my solved equation, I found a rise and a run. Okay, good. And in my solved equation, I have a place for that rise and for that run. So now we just got to sub in our variables, okay? So the m, the mass of the target glider, is going to be equal to, like we said, the mass of the bullet glider times run over rise. Subtract the mass of the bullet glider. We have all of those variables. The question gave the mass of the bullet glider as 500 grams or 0.5 kilograms. We just found the run to be 2.4 meters per second and the rise to be 1 meter per second. Look at that, meters per second cancels with meters per second. We're going to be left with units of kilograms. What are we looking for? A mass. Very good. We should be getting units of kilograms. Okay, and when I plug that all into my calculator, I got 0.700 kilograms, which within reason is about the same as what I got on my solutions on the answer key. Okay, plus minus about 30 grams. Again, it's kind of an iffy graph, so it's reasonable that just small estimations end up with a pretty big difference, and especially within probably the error bars of our experiment, I would say that's reasonable. Okay, so what did we do? Let's review. we had a graph. We knew we were going to have to do graphical analysis, right? It asked for the mass of the target glider. So we said, what equations relate those things? What equations relate the combined velocity of that they move with after, the velocity of the bullet glider, and the mass of the target glider, right? You already probably should have been thinking this just because it is a collision, but even if you weren't, you're saying the mass, the velocity before, the combined velocity after. That's starting to sound like the equation that relates them is just going to be a conservation of momentum, right? Sure enough, when we plug it in, look what popped up. Our required, our x variable, our y variable, right? This is looking good for a graphical analysis setup. So then we manipulated for our required, like you always do, and then we said, what are we doing with our x and what are we doing with our y? We're dividing our x by y. Now, admittedly, you hadn't seen that until Physics 30, but you know how to find a run, you know how to find a rise. It's the inverse of the slope, okay? So you go find them, you plug them in, and the rest is history, okay? Now I can hear some of you saying now, what is the point of doing this with graphical analysis, right? Seems like we're just forcing graphical analysis, okay? And it might seem that way, but remember, this is an experiment with a whole bunch of trials, right? We gathered a lot of data. This is a good method. This brings us closer to reality, right? If we think of this in a practical sense, when you're really doing science, you need to be gathering a whole bunch of data, and then with graphical analysis, you can find the trend of that data instead of just taking one measurement, writing down those numbers, and hoping you didn't mess up that one trial, right? Do a whole bunch of trials, let the trend emerge, and then you can trust your results a lot better. That is the power of graphical analysis. That is why we're doing it here. We're not just forcing it for the sake of it. Okay, hopefully that helped.